If I get corona, I get corona. At the end of the day, I'm not gonna let it stop me from teaching computer science. I've been waiting for the spring break for a while. For 2 months I had these lectures planned, 2 or 3 months. I'm just out of here having a good time. I hope you guys know what I was referring to. I was referring to that college student who was saying that partying is much more important for him than coronavirus.
If I get corona, I get corona. At the end of the day, I'm not going to let it stop me from partying.
Which I'm not sure if you know, but he recently had to apologize for. So he said that, like, he said sorry, like, for the comments. He was mostly apologizing for the insensitive comments versus the actions, the partying and the spreading the coronavirus. Okay, so I definitely don't want to defend him. What he did was absolutely, there has to be politically correct phrase here. His actions seemed immature. Oh, perfect. Politically correct phrase. Yeah, so his actions seemed immature, but at the same time though, that's the most honest answer which you can expect. You catching a person in the middle of doing something like bad, and like, what is he supposed to say? Like, so so many students, what are they supposed to say? Like, if you expected some honest answer, that was the most honest answer. Like, for me personally, he said, what he meant was, coronavirus is not as important as having fun. The coronavirus was exaggerated for him personally, in his opinion, right? It's not that dangerous, and he's just have been planning that trip for so long. Like, why would I have to postpone that? Why would I have to do anything with it? In his opinion, again, his opinion. And that was super honest, like super honest. And he had to apologize for that. And it's interesting again, because like in the text, he said, like, I apologize for the actions, but the severity of the comments, that was the worst thing. And like he just got unlucky, in my opinion. Like, he got on the news, and that was the first thing like in that section of the news piece, right? So there were so many people talking about it, but the way he said it, was eye-catching. It was a bold statement. If I get corona, I get corona, and then it just got spread out like everywhere. And but again, like, he was super honest, and there were so many people like doing that, but he was unlucky and he got attention. Yeah. I have a question, by the way. So those people who were editing the news, okay, so they know that they shoot for NBC, CBS, like that channel. They know that a lot of people will be watching that. They also know that nobody is going to support this guy, right? So nobody's going to support that thing when you say, like, I don't care about the disease which the whole world is going down for. Okay, nobody's going to support that. So if he's 21, if he's partying at the Miami Beach, he's probably drinking. If he's drinking, he's probably 21 years old. Well, let's say he's 21 years old. If he's 21 years old, he's probably senior or junior, which means he's probably graduating soon. And now he got on the news, and he became so popular. Okay? So if people who were editing the news, if the point was to show that there are college students who don't listen, or let's say the government has not, or the colleges, the Miami government did not do good enough job to keep them safe, if that was the point of the news, then they wouldn't have to put his name out there. So the people who were editing, right? My question is, how moral, how sensitive is that they put his name out there? They put the very, very strong statement first, right? Out of all the interviews, they put his face first, his statement first, right? And he had some sunburn. He's not in the best shape. So they were like demoralizing that person, the guy, and they put his name out there. They put his name, okay? So how moral is that? If he's graduating soon, he may not be able to find a job because of that. If there was no name, at least, if the face was changed, the voice was changed, then they'll be fine. And that would still make the point that the college students are not listening, they don't care about the coronavirus. And even if they put exactly the same phrase, right? But they put his face there, they put his name there. And now when a company is about to hire him, they'll probably run a background check, and where is his name going to pop up? Good luck starting the career. So my question is, how moral, how sensitive is that? Because I know I know that making that point was not the purpose. The purpose is to get as many views as possible. How do you do that? You just like get the phrase out of the context. Okay, so like you need to create something like eye-catching. You need to create something which will draw attention. Because I remember I was giving interviews to TV as well. So they would, usually the way it goes is that they would ask you like that many questions, let's say 10, and then we'll just like cut it and edit, and they will pull something out of the context, and hopefully they'll be like exactly what you meant. He might have been talking there for I don't know, 20 minutes, 10 minutes, and he might have said a huge amount of different stuff, but they pulled out like a very, very tiny, like one, I don't know, 3 sentences, and which completely demoralized him. And now he showed him from a horrible perspective. So my question would be to those people who are editing that, how sensitive is it? And how moral, how ethical is that? Anyway, lecture number 21, let's roll the intro. Today we're talking about binary search trees again and again. They're very, very, very important, crucial. Today will be a bit, I guess, a shorter lecture, but I want you to have more time to practice with yourself. And I'll explain you what I mean in a second. Okay, so let's get back to the slides. Read chapter number 25. Today we'll be talking about binary search trees. So the plan for today is this. I'll be talking about, again, tree traversals, 3 types of them, all of them. One more time. I definitely want to make sure that you understand, guys, how they work. Also, and that'll be it. After that, you will just practice for yourself. I prepared a few, which is 1, 2, 3, 4, 5, 6, 7. Hold on. 6. Okay. Yeah, it looks like 6. 6 exercises. All of them are pretty difficult. I think if you solve like at least 1 or 2 of them, they'll be good. 1 of them will become your homework, or maybe 2. Also keep in mind that starting from today, you definitely need to take notes, because you will need to submit them for your homework on Monday. So next Monday for the homework, you need to submit the notes. That's why don't you take the notes right now as you're watching this video. Anyway, binary search tree. Okay, so tree traversal, what is that? That is a process of visiting each node in the tree exactly once. Remember arrays, right? Traversing an array, that means you visited each element, each like number in the array exactly once. You go from left to right, or right to left, or like from the middle, and then like go, I don't know, to the edges. It doesn't matter. Tree traversal, same thing as traversing anything else, because traversal also exists in graphs, and that's what we'll be talking about in 318 class. That means visiting each element of the data structure exactly once. In tree traversal, those elements are nodes, vertices, right? Visiting each node exactly once. That's what tree traversal means. Tree traversal is the process of visiting each node in the tree exactly once. There are several ways of doing that: depth first and breadth first traversals. Okay, we'll don't think about them yet, but most importantly, we will focus on in-order, post-order, and pre-order traversals. In-order, post-order, pre-order traversals. Okay. Yeah. So, with in-order traversal, what happens is the left subtree of the current node is visited first recursively. Okay, so let's imagine that recursively was not there. So let's imagine that left node is visited first, then the current node, then the right subtree is visited third. Okay, so in other words, the same formula. Okay. So left, then current, then right. Okay, so LCR, left, current, right. Imagine you have a tree. Let's say it is a binary tree, not binary search tree, but just binary tree. Okay, so that's 1, 2, 3. Okay, let's imagine that you have like that few nodes, only few of them. Okay, and let's imagine that you have the values associated with them. Let's say that's 10, let's say that's 19, and let's say that's 20. Again, not a binary search tree, just a binary tree. In this case, what's going to happen is this. you first visit the left node, okay? So imagine that recursively as a order was not there, okay? And then you visit the first node first, which is 19, you print it out. Then you go to the current node, which you start with. You always start with the root. So that's 10. And then you go to the right and you print it out, which is 20, okay? So that's cool. However, when you add the word recursively, what happens is that if 19, so again, the first subtree which you visit is left, right? Then when you go from 10 to 19, if 19 also has children, then you cannot print out 19 yet, you need to go deeper to the left from 19. So that's what recursively means. So that means so if you go to the left, that means you just go to the left. If you go to the left recursively, that means you go to the left, and then you go to the left of the left, then you go to the left of the left, you go to the left of the left, and you're basically going to go to the left as long as you can. Which means that if you have, let's say, okay, so let's say that's kind of the binary tree we have in. Okay, if that is the current situation, again, if the recursively was not the case, if the recursively was not there, then it would just go from 10 to 19, print out 19, okay? But if we say recursively, that means you don't stop. That means you just go to the depth as much as you can. So you go from 10 to 19, from 19 to this, from here to here, to here, to here, to here, and then you would also go from here to the left. The problem is that nothing exists to the left. Okay, so you would try to go, if it was possible, you would go there, but just there is nothing there. That's why the first element you printed out would be this guy over here. Okay. So, and then after, yeah, and same thing for the right subtree, right? So if you were visiting the right subtree first, for example, and if you were doing that recursively, there'll be exactly the same stuff. You would just go strictly to the right as much as you can. Okay. Yeah, so I'm thinking how else can I explain it better, because I know it can be confusing. I don't know. Let's maybe. Well, yeah. Okay. So let's finish with this, and then we'll just dive into examples, and maybe I'll provide a lot of examples, and then it'll maybe make more sense. Okay. Okay. So what do we have here? We have something like this, and then let's say this guy has a child, right child, and this guy has a child as well. Okay. I'm not gonna give them any values, but let's say this is the situation. Okay. So again, the idea is we need to visit the left subtree first. Okay, and we're doing that recursively, which means we just need to go like way down to the left, to the down towards bottom left corner, right? So we go from 10 to 19 to over here, over here, over here, over here, over here, and then we'd also go to the left, but like there is nothing there. So that's why we print out this number first. Okay. So now we visited the left subtree of this node, right? So we visited left subtree, then we print out the current node, this guy, and then we print out the right subtree, which doesn't exist. Okay, so we don't print out anything here. Then, so now, if we consider this tree, right, that is a left subtree for this guy. So for this guy, we printed out the left subtree completely. Now we need to print out him itself, and then we need to go to the right. Okay, which is nothing, so we don't print out anything here. Now, we finished with this. We finished with this tree. Okay, we finished with this. That is a left subtree for this guy. So we're done with this subtree. We print out this guy itself. Okay, and then we'll go to the right. So this guy is actually exists. Okay, so we'll print it out. Perfect. Now, after that, we finish up with this whole tree, subtree. That is the left subtree for this guy. So we printed out left subtree of this guy. Now we need to print out this one and the right subtree for this guy, which doesn't exist. Okay, so nothing there. After that, we are done with this subtree. Okay, so which happens to be left subtree of this guy of 19. So for 19, we printed out, we basically processed or traversed the whole left subtree. Now we print out 19, and then we print out this one, this node over here. Okay, after that, we happen to be finished with this entire thing, okay, which is the left subtree of 10. When we finished with the left subtree of 10, we need to print out 10, and then you need to go to the right from 10, which is 20, print out 20, and that's it. And then we're done with the tree. Okay, hope it makes sense. Now let's dive into examples. Okay, so let's see what happens here. Let's see what happens here. Okay, so again, if we do an in-order traversal, we'll go to the left, but we do it recursively. Okay, and then once we finished with something on the left, then we just go like one step up, then go to, print that out, and then go to the right, and also do that recursively. So it means go to the right and then go to the left from that right. Anyway, so let's see what happens here. First off, we go from A to B, right, to the left, right? Then we go, since we do it recursively, we need to go to the left from B, which means we go to over here. And then since we again do it recursively, we need to go to F. And then since we need to go recursively, we'll go to the left from F, but there is nothing there. Okay, so that means we stop. Okay, so the first node we print out would be F. Okay, F. At that point, we're done with the left subtree of D. Okay, and if we're doing in order, left, current, right, we need to print out D. After that, hold on. We need to print out D, and then we need to go to the right from D, so left, current, right, which is G, right? After that, we would have to recursively go left from G, because again, like when we come to G, just kind of, since it's a recursion, the whole thing like starts over again. We need to go to the left from G and then just repeat, kind of like, you see, it's a like, I don't know, like a cabbage or onion. So you have a layer, so like onion inside of the onion, inside of onion, inside of onion, inside of onion. And like whenever you come to the new node, new tree, you kind of reset yourself. You need to go to the left, current, right. So there is nothing from G, that's why you're done with that very quickly. Then you print out G itself. Then you go to the right from G, because it's left, current, right, and there is nothing. Okay, so at that moment, F, D, G, you're basically done, like you finished processing this, okay, which is the left subtree of B. So after that, left subtree of B, B itself, and then you need to go to the right from B. You go over here to E. Okay, so you go to E. The problem though is that again, since when we come into E, we restart the whole thing, we repeat it again. We need to go from, we need to again recursively go to left from E, which is L. So we need to go over here, and ideally then we need to go to the left from L, which is nothing, which doesn't exist. Okay, so after that we print out L. Okay, and then we print out E. Okay, so left, current, and then we need to go to the right. Okay, but it doesn't exist, so that's why, that's it. Now at that moment, we printed out left from B, B itself, right from B. Okay, so we're basically finished. We're done with this. Okay, in other words, we're done with the left subtree of A. Okay, so we printed out left subtree of A. Now it's turned for the A itself. No, hold on, sorry. No. Good. I'm good. No. Hold on. Yeah, okay, cool. So we finished with A, right? I can delete it. Sorry, 1 second. Okay, we finished with the left subtree of A, then we print out A, and now we need to go to the right from A. Okay, so we come to C, and we restart the process. From C we go to the left, go to the left, go to the left. Okay, so from C we go to R. Okay, from R we go to the left of R, which doesn't exist, right? So then we print out R. Then we need to go to the right from R, which also doesn't exist, so like we're done with R. then we'll go to the C, and then we're done with R, C, then we need to go to the S, okay? And that's pretty much it, right? Yeah, and that'll be it, okay? Then you're done with, like, you're basically done with the right subtree of A, right? So you did left subtree of A itself, and then right subtree of A, that's it, okay? So that is in-order traversal, okay? Exactly the same thing applies, exactly the same strategy applies to post-order and pre-order traversal. You just need to change the sequence, the order, okay? So for in-order traversal, you go left, current, right. For post-order, you go left, right, current. For pre-order, like you're being selfish, you care about yourself, that's how I memorize that. You go current, left, right, okay? So for the post-order, how does that work? Left, right, current, I think. Yeah, okay. So you go to the left, then you recursively, right? So you go to the left recursively, then you go to the right recursively, then you print out itself, okay? So that's why from A you go to B, from B you go to D, from D you go to F, okay? From F you would go left, but that doesn't exist. Then instead of going to F, you would go to right of F, which doesn't exist either, and then you print out F, which means that the first letter will be F, okay? And then, so left, right, current. So left from D, and then right from D, okay? Then again, like to look at its children, which don't exist, right? So that's why we'll go F, which is left, G, which is right, okay? And then D, which is node itself. At that moment, what did we finish with? We finished with the left from B. Okay, so for B, we finished with the left of B. Now we need to go to the right from B, which is what? Which is here. But since it is recursive, again, you need to repeat the whole process. You need to go to the from E to L. Okay, print out L. Print out L. So for E, left would be L, right doesn't exist. So L, nothing, E. Okay, L, nothing, E, okay, and at that moment, what did we do? We finished traversing left subtree of B, right subtree of B, and now it's turn for B, because we do left, right, current. And now we do B. Okay. Cool. Yeah, so we finished with this. At that moment, what did we do? We finished with the left subtree of A. Now we need to go to the right subtree of A, and then we'll come to A, and that will be like our stopping point. Okay, so we'll go from A. Yeah, so we'll go from A to over here, then. Yeah, then we restart the whole thing again. So from C we'll go to the left, then we'll go to the right. So we'll print out R, then S, then C. Okay. And after that, we'll basically finish with this, with left subtree, right subtree of the entire tree, and then we can print out A as our last point. Okay, and that's it. So that will be the post order for this tree. And now pre-order. Pre-order means you're selfish. Like post order means you're not selfish. You kind of like you care about the left, right. So you care about your children first, and then you print out yourself. Pre-order means you care about yourself first, and then you print out your children. Okay, so the strategy is left, sorry, current, current, 1 second. Current, left, right, okay. Okay, yeah. So what happens here is that the first we'll always start with the root, with the root, right? The first node we visit is A, and since it is current, immediately print it out. Immediately. Okay, so we'll go A, then we would go left, which is B, and then again the whole thing starts again. So current left right with respect to B. Current left right with respect to B, current which is B already, immediately print out B. Okay, then we go to the left from B, immediately print out D. Then we go to the left of D, immediately print out F. Okay, then Okay, so we finished with F, and now here's the kind of like maybe tricky part. So we finished with F, then we climb back up to D. So for D, when we think about the root, the tree for D, right? We printed out D itself, printed out left from D, which is F, and now it's turned for right of D, which is G. Okay, so print out G. Now that point, right? So we're done with the So now if we think about B, the tree for B, we print out the left subtree of B. Now it's time to go to the right. So we go to the right from B, which is E. Since it's current left right, immediately print that out. And then we'll go to L, which is the left. Then we need to go to the right from E, which doesn't exist. So that's it. We're done. Now here, if we think about A, right? If we think about A as a tree. So what just happened? We printed out A, right? That's our A. We printed out the whole left subtree from A, okay? So that's B, D, F, G, L. And now we need to print out the right subtree of L. So we need to go over here to C. Since it's current left, right, immediately print out C. Okay. Then we need to go to the, so it's current left, right. We print out then R, okay? And then print out S. And then S. Yeah, and that's it. And then we're done with the whole tree. So that's pre-order. That's pre-order. Hope it makes sense. We'll be talking about 318 as well. Anyway, so what problems did I prepare for you? So there is a very popular website, hackerrank.com. Basically, that website contains problems for computer science. They may be a bit difficult for you guys. Well, it's kind of like the complexity of the homework, I would say. But what's very nice about this is that so hacker rank. So hacker means hacker, person who's good in computer science. Rank means ranking them. Okay, so there's a ranking of hackers. The idea is that they give you a problem, you solve it, you submit it, and it automatically checks the correctness of your code right there. So for example, yeah, and it's like but in the way they describe it is very, very, very formal. It's very similar to documentation. So you probably saw like very long words, very long description of something which is very simple, right? But it's something which you guys also have to learn how to read that official documentation of anything. Okay, so for example, is this a binary search tree? Okay, so the purpose of this challenge, okay, we define a binary tree to be a binary search tree with the following ordering requirements. Okay, so now they provide the requirements of what does it mean to be a binary search tree. Okay, so the idea is this: they give you the input, okay, and the data will be between 0 and like 10,000. And we're responsible for printing output. A function must return true if the tree is a binary search tree, otherwise it must return false. Okay, so they give you the tree and you need to understand if that is a binary search tree or not. So for example, in this case, if that's the input, right? So, okay, so that's not a binary search tree, right? Because 5 is less than 3, 5 should not be on the left. 4 is less than 3, 4 should not be on the left. 6 is less than 2, so that doesn't make sense. Like 6 is greater than 3, that's good, but 6 is less than 2. Okay, so the output is no. So then here you change to Java, like any kind of Java, and yeah. So you can run the code, you can submit the code. Okay, but I think first off you will need to create a account here. Okay, so I prepared a couple of examples for you. They're kind of like, again, with the same difficulty as the homework. Okay, yeah, and a couple of problems from the book. For example, a full binary search tree is the binary tree with leaves on the same level. Okay, that's actually a very, very good concept to know as well. So imagine that you have a binary search tree. Okay, and imagine it looks something like this. Okay, so that's kind of so that binary search tree is not considered to be full. Why? Because what are the leaves? This guy is a leaf and this guy is a leaf. They are not on the same level. Not on the same level. If I have a full binary search tree, it's gonna look like this. It's gonna look like a triangle. Sorry, it's gonna look like this. So like all of them, all the children are going to have like exactly the same amount of nodes. Okay. So here, what leaves do we have? This guy, this guy, this guy, and this guy, and they are on the same level. You see, they're on the same level. So that's considered to be full binary search tree, which is kind of like the, I don't know, more even structure, like triangle, more. The idea is that if I have a full binary tree, finding an element there is a lot easier than in a binary tree, which is like that, like shape, ugly shape. So this beautiful shape is considered to be like full binary tree, where all the leaves are exactly on the same level. Okay, so level, in case you forgot, level is the distance between the node and the root. Okay, so the level of these leaves is 2, like 1. Because it's 2 edges away from the root. Okay. Yeah, cool. So the question is, like, for example, you're given a binary search tree. How do you make sure that that binary search tree is full binary search tree? So you need to return true if that binary search tree is full, and you need to return false if binary search tree is not. If binary search tree is not full. Okay. Assuming, yeah, so you don't have to check if the binary search tree is actually a binary search tree, right? So you kind of assuming that it's already been checked. Yeah, so that's an example, very good one. Okay. Inorder traversal without recursion, right? So last time we talked about Inorder traversal, and then we gave you the code for Inorder traversal, but it's also possible to do it without the recursion. Without recursion means with the loops. And as a hint, you're going to use the while loop. While, not for, not do while, but while loop. Okay, create a method which returns number of non-leaves. Okay, so yeah, like, I don't know, imagine that you have a binary search tree like this. Okay, so it's not a full binary search tree, just a binary search tree. Okay, so in this case, the question is how many non-leaves do you have? So how many leaves? 1, 2, 3, and then number of non-leaves would be like 1, 2. Okay, so these two guys are non-leaves, so the answer to this question for this particular tree will be 2. Okay, so the idea is pretty simple actually. You just need to check if the node you're at contains any children, has any children. If it has at least one child, then it is not a leaf, and then you need to increment some kind of global counter. If the node you're looking at doesn't contain any children, then you do not increment the counter. So basically you do Inorder traversal, for example, or any other kind of traversals, and you use a traversing. As you traversing the nodes, you are either incrementing the counter or you're just not incrementing the counter. That's the idea. Okay, I do not want you to limit to any number of exercises, and I do not want you to force you to do them. Just my recommendation to do as many as you can, especially if you do them on hackerrank.com, because in that case they will automatically check if your code is correct. When you submit it, it automatically tells you like, hey, your code is correct, because they actually create like, I don't know, 20 test cases or 16 test cases, and they'll be able to tell you like, hey, yes, like your program successfully passed all the test cases. That means your program is correct. Okay, hope it makes sense. I'll see you guys on Thursday. Have fun. Bye bye.